Hello and welcome to this video on how to interpret latent class analysis with covariates. My name is Geiser, I'm an instructor for QuantFish, and on this channel I present weekly statistics tutorials. I often talk about latent variable models, including structural equation models, factor models, and latent class analysis. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including courses that I offer through QuantFish. In this video, I want to explain how to interpret the results of a latent class analysis with a covariate. This is something that many people find confusing and they're not sure how to interpret the output that they get from their computer software. And so I want to walk you through this here step by step with a simple example. In my example, there is a latent class variable with two classes. The latent class variable is based on a set of items that measure computer game preference. So individuals were asked about different types of games, including action games, logic games, skill training games, simulation games, and driving simulator games. And so they were asked to rate whether they do or do not play these types of games. And so based on that set of 6 items, or 5 items, a latent class variable was extracted with 2 classes in this case, and I'll show you in a minute what that solution looked like. So now in the next step, the idea is to look at whether gender predicts class membership, or in other words, is there a difference in latent class assignment for males as compared to females? Are males overrepresented in one of the classes or females? And so I'm adding gender here as a predictor variable of the latent class variable. Now, first of all, let's take a look at what this 2-class solution here looked like. And so in this example, in the 2-class model, we had class 1, which had a low probability of playing any of the 5 games. You can see class 1 here in this profile plot at the bottom. You can see that there were low probabilities of below 0.2 for any of the games. So this class was interpreted as a non-player class. In contrast, class 2 was a class with a higher propensity of playing computer games, and in particular simulation games. You can see that the probability that individuals in this group endorse these items was fairly high, over 0.6. So in other words, class 2 was interpreted as a player class and class 1 was interpreted as a non-player class. And so now we're going to relate these 2 classes to gender by adding gender as a covariate to our latent class model. And here I did this in the Mplus software, which is a very convenient program for running latent class analysis, and many types of other mixture distribution models, including latent transition analysis, latent profile analysis, factor mixture modeling, growth mixture modeling, and other kinds of mixture models. So I ran this here as a classical latent class variable, and I'm showing you only that part of the output that relates to the covariate analysis, which you can see here. So you can see that Mplus has a section in the output that is labeled categorical latent variables, and in this section there are coefficients that are reported. You can see that the first one here is L#1 on gender R. So gender R is my gender variable, and the R at the end is for recoded, because I had recoded the gender variable from a previous coding scheme for the purposes of this analysis. So that's not really important to know. It just explains why gender has a double R here at the end, so that's not actually a typo. And then L#1 refers to the latent class variable, which here was labeled as L, and so #1 is for the first class versus the reference class. And so in this scenario here, where we have only 2 classes, there's only one threshold, so to say, or one contrast, namely between class 1 and class 2. There's no L pound 2 or L pound 3, but that would be the case if you had 3 or 4 or 5 classes. So now what does this mean? The L pound 1 on gender coefficient here, this is actually a logistic regression slope coefficient that I indicate here as beta 1, 1. And so Mplus reports this logistic regression slope coefficient for the regression of the latent class variable on gender, along with a standard error, which you can see here in the next column. 0.558 is the standard error, a Z statistic, which is a test statistic for testing the null hypothesis that the coefficient is 0 in the population. And you can see that that null hypothesis here could be rejected at an alpha or significance level of 0.05 or even 0.01, because the p-value that's reported at the very end here, 0.000 something, is very, very small. So this means the coefficient of negative 4.064 is statistically significantly different from 0. And that already shows us that there is a relationship between gender and the latent class variable. So gender is significantly correlated, we could say, with class membership, because this coefficient is statistically significant. Now, that still doesn't tell us or say anything about in which way this is related, and so we have to look into this in more detail. But first of all, this tells you what that is. And then second, we have an intercept here for L pound 1, and this is the logistic regression intercept coefficient beta 0 or beta 01 here. And so we will also learn shortly what this intercept coefficient tells us. So in summary, based on this output, we can set up our logistic regression equation for this latent prediction model of latent class membership on gender. And so this looks as follows. So in a logistic regression model, which here is formulated for the log odds, or logit as we say, the log odds is here the natural logarithm of an odds. So log gamma 1 over gamma 2 is the logit or log odds. And so gamma 1 refers to the probability of being in class 1, which is here the non-player class, and gamma 2 is the probability parameter for being in the second class, which here is the player class. And so this can then be rewritten as log probability of being non-player over probability of being player. So this log odds is considered in the logistic regression model, and in a logistic regression model we have a linear model for the log odds, which you can see here. So then on the right hand side we have the intercept 2.582 minus the slope 4.064 times gender. So that's our regression equation for the log odds in this logistic regression model. And so we can set this up based on the Mplus output. Now, of course, you're not satisfied at this point, because you're still wondering, what does this all mean? I only now understand that we have a significant slope of this logistic regression, which means gender is significantly related and significantly negatively related here to class membership. But what the heck does this mean? So let's take a look at this in more detail so we can understand what exactly these coefficients tell us. So here again we have the logistic regression equation one more time, the log odds on the left hand side, and then on the right hand side we have our intercept beta 01, and we have the slope coefficient beta 11 times our predictor gender. Now the first thing that we have to look up or understand is how is gender correlate? How is gender coded? What is the coding of the categories of gender? If we don't know that, then we cannot interpret these results at all, because it entirely, so to say, depends on what category of gender is coded in which way and in which order and so on. So in this case, we have to know that females are coded as 0 and males are coded as 1 on this gender variable. So it's a dummy variable, a 0, 1 binary variable with 0 for females, 1 for males. And this is arbitrary. We could have chosen 0 for males and 1 for females. It doesn't matter for the purposes of this analysis. The only thing that matters is, or what we should do is, we should really have a 0-1 coding and not a coding like 1 for female and 2 for male, which I had initially, and that's why I recorded the gender variable. That's why it's called gender R in Mplus, because I coded a gender variable from 1, 2 to 0, 1. And the reason why this is better is because when you have a 0-1 coding, then your intercept is meaningful, and the whole interpretation of the set of coefficients is easier and more intuitive, makes sense. Whereas when you have a coding of 1 and 2, for example, then the intercept is not interpretable, and then the whole thing becomes more complicated to interpret. So this is what this looks like. And so then what does this mean for our intercept and slope coefficients? How are they interpreted? So we have to know that the intercept coefficient beta 01 is related to the odds in the group that's coded 0. And specifically, if we exponentiate beta 01, our intercept coefficient, then this gives us the odds in the group that's coded with 0. And in this case, that's females. So exponentiating 2.582, our intercept is equal to the odds of being non-player as compared to being player in group female. So non-player is the first class, player is the second class, and Mplus always uses the last class as reference. So this gives us the odds, this odds in group female. And so you can see that the odds of being non-player as compared to being player then are large in group female, 13.22. So females are a lot more likely to be non-players than to be players. So this already tells us something, right? So that's more interpretable than the number 2.582 per se, which is not really interpretable so well. But when we exponentiate this, then it gives us the odds in group female, and the odds in group female has a straightforward interpretation. Now, what about males? In order to get the odds for males, we have to exponentiate the sum of the intercept beta 01 and the slope beta 11. So beta 01, here's the intercept, plus beta 11, exponentiating that sum of coefficients gives us the odds in group male, and you can see the odds in group male of being non-player as compared to being player are 0.23. So that's more difficult to interpret because it is smaller than 1, right? This way around. So it's not really easy to express in words, but it shows us that males are much more likely to be players than to be non-players, because here we get a small number, as a number smaller than 1 here for the odds of being non-player as compared to being player. So that already shows us that there is a gender difference in the direction that females tend to be non-players, males tend to be players in this example here. So what makes this even clearer is the so-called odds ratio, which can now also be computed based on the odds for the two gender groups that we just looked at. So we can look at the ratio of the two odds, which you can see here as OR. OR is the odds ratio, and I have the ratio for males in the numerator and the ratio for females in the denominator. So I'm dividing 0.23, the odds for males, by 13.22, the odds for females. And that's equivalent to exponentiating the logistic regression slope coefficient beta 11. So if we exponentiate negative 4.064, that also gives us the odds ratio, and that's more straightforward than first computing the odds and then computing the ratio of the odds. You can just simply exponentiate beta 11, in this case negative 4.064 exponentiated, and that gives you the odds ratio. And so here the odds ratio is 0.017. And so an odds ratio is a measure of association where When the odds ratio is 1, this means there's no association. So unlike a correlation coefficient where you would look for whether this is different from 0, here you look for whether it's different from 1. And so here the odds ratio is different from 1. It is smaller than 1, indicating that there is an association. Now, an odds ratio smaller than 1 is kind of difficult to interpret because it is in the same way as the odds. When you have something that's smaller than 1, then it is hard to express that in words. However, a logistic regression model is kind of symmetric, so we could look at the odds ratio, so say the other way around, to make it more interpretable, and specifically we can look at the different reference class. So rather than looking at the player class as reference, we could look at the non-player class as reference, and that makes the odds ratio more interpretable. So let's look at that as well. And it's one very nice feature of Mplus that Mplus provides the results for different reference classes. So when you have a model with multiple classes, Mplus will give you the results for all classes as reference. And that helps because some reference classes are more interpretable than others. So now we're using class 1 as reference as opposed to class 2. And so we're now using the non-player class as reference, and you can see that in this alternative parameterization that Mplus also calculated, we get the same coefficients, however with a different sign. Now our slope coefficient is positive 4.064. Previously it was negative 4.064. And the intercept now is negative 2.582, whereas previously it was positive 2.582. So it shows you that the logistic regression model is symmetrical, and it doesn't really matter what class you select as reference or what gender group you select as reference. You only have to know, so to say, what the respective reference group is so that you can properly interpret the results. But really, so say, for the absolute value of these coefficients, the coding does not matter. However, it does matter for the odds ratio. So now we have the odds ratio relative to non-players here. So the non-player class is now our reference class. And so again, we have the odds for males here in the numerator and the odds for females in the denominator. However, we switch the order of the classes in the fractions above the major fraction here and below. And so therefore we get a different odds ratio, which again is the exponentiation of our logistic regression slope coefficient, which is now positive 4.064. And so when we exponentiate positive 4.064, we get a different number. It's no longer 0.017, it's now around 58. So about 58 is now our odds ratio, and that's a lot easier to interpret because it is greater than 1. And so you can see that Mplus in fact gives us the exact odds ratio also here as 58.181. So you don't have to calculate it by hand. Mplus will give you the odds ratio for any reference class, which is nice. Now, how exactly do we interpret the odds ratio? The odds ratio we saw that way is 58 with the non-player class as reference, and that's very interpretable. We can interpret that as saying the odds of being player as compared to being non-player are about 58 times greater for males than for females. And that's very, very intuitive in terms of the interpretation. It shows us that males are more likely to be players than females, and females are more likely to be non-players. And an odds ratio of 58 is of course a large effect. We saw from previous results that it's also statistically significant. The logistic regression slope coefficient was significant, and so that means then that also the odds ratio is significant. We also get a confidence interval for the odds ratio in Mplus, which you can see on the previous slide. At the bottom you can see there's a 95% confidence interval here, which ranges from 19.478 to 173.792. This is a pretty wide confidence interval, which has to do with a large standard error here. This is such a huge effect, and so there's also a large standard error. As a result, the confidence interval indicates that the precision of the estimate is not very good. However, the interval does not include 1, indicating that the odds ratio is statistically significant. So again, an odds ratio of 1 would indicate no relationship, and here the confidence interval does not include 1. So this means that the parameter is significant at the 5% level, which we already saw from the significance or from the p-value here for the logistic regression slope coefficient. Now, some people find an odds ratio nonetheless to be somewhat difficult to interpret because it does not show us the exact probabilities for each group. So it does not, for example, show us, do we have 80% males in the player class, or do we have 60% males in the, so what are really the differences? So the actual differences between the groups we cannot see from the odds ratio. So it's somewhat complicated still to interpret in a way, maybe not so intuitive, and so therefore another nice feature of Mplus is that it will also give us the exact probabilities for each group based on the logistic regression model. And so you can get that in Mplus in a so-called probability plot, where Mplus will show you for each group what the class probabilities are. Now let me explain this graph to you. So here you can see the red line is the non-player class, and the blue line indicates the player class, and then on the x-axis you have females as coded as 0 on the left-hand side and males coded as 1 on the right-hand side. And now you can see that females have a low probability of being players. So the probability would be here, it would be smaller than 0.10. And they have a high probability of being non-players, as you can see here. So this probability is probably somewhere around 0.9-ish for being non-player in group female. In contrast, males have a small probability around 0.2 of being non-players, and they have a high probability around 0.8 of being players. And so that is very intuitive to look at those probabilities. And what's even better is that Mplus will also give you the exact data from the plot. If you ask for it, you can save the probabilities that are depicted in the plot into a file. And so I did that, and then you can see here that we have in this file females in the first row coded as 0 and males in the second row coded as 1, and then the probabilities for class 1 in the next column and the probabilities for class 2 in the last column. So here you can see that females have a probability of 0.92967, so a 93% chance of being non-players, whereas males only have an 18.5% chance of being non-players. And then with regard to the player class, females have only a 7% chance of being found in the player class, whereas males have an about 81% chance of being in the player class. Now this is a somewhat extreme example. So in this sample, that was the case. There was a huge gender difference with regard to computer game preference. Probably in most samples there would be a more even split between males and females. So this was a specific special sample, and with a pretty dramatic gender effect with regard to a computer game preference. Now, you can do the same kind of analysis also with a continuous covariate. So you could have, for example, age as a covariate or some other continuous variable, and then the interpretation of the logistic intercept and slope coefficient would be somewhat different, but the principle would be the same of this interpretation. And you could also get the same probability plot in Mplus to look at the probabilities across different values of the covariate, which is very useful to interpret the results of a covariate analysis, in particular when you have a continuous covariate where odds ratios may be even trickier to interpret. I hope you found this video useful to learn more about the interpretation of logistic regression results in a latent class analysis with covariates. If you did, then please consider subscribing to this channel, hit the like button, and don't forget to check out the description for additional resources, including courses on latent class analysis and mixture modeling that I teach for QuantFish, and I'll see you next time.